Uh, so the pad footing is subjected to axial load and the bending moment. So basically what happens is in addition to the axial load, we get a bending moment about one axis. And then you have to actually look at the section modulus. Section modulus is this L, breadth is B. So Z is B L square divided by 6. And when the bending moment is M, the maximum stress due to bending moment can be found by dividing MO by taking MOVZ. And so you'll end up with a stress distribution like this. And so we have to see how we deal with this. The only thing is when you find the bending moment, you have to find it using this side, because this side the pressure is lower. And when you are finding the shear also, you have to use this particular side. But the problem comes when you try to deal with the punchy shear, where the punchy shear perimeter is on both sides. So you have to see how we deal with that. So we'll consider an internal column footing of a building supports a 450 millimeter square column. Size of the base has been selected as 3600 by 3000 millimeters, because the bearing capacity of the soil has been considered as 140 kilonewtons per meter squared. And we are using 25 megapascal concrete and 500 megapascal reinforcement. And the depth has been selected as 550 millimeters. You can see it's not an excessive depth. Depth has been selected as 550 millimeters. So the loads are like this. You get a dead load of 770, that is the permanent load, and the variable load is 330. And the moment values are 78 and 34. So due to the permanent loads, you get a bending moment of 78, variable loads, you get a bending moment of 34. And if you look at the weight of the base, and it is 148.5 kilonewtons. So the total axial load is 1248 kilonewtons. And if you look at the axial stress, we have to divide it by the area. 1248 divided by 3.6 divided by 3 will give us 115.6. The bending moment, addition of these two bending moments is 112. And when you divide 112 by Z value, the section modulus is Z, given by BL squared by 6. Here you can see the section modulus is also found. That is 6.48. The area is 10.8. The stress due to bending moment is 17.3. So the maximum stress will be 115.6, that is axial, plus the bending stress 132.9, and on the other side you get a lesser value, that is 115.6 minus 17.3. So those are the values, and the important thing for us here is to ensure that you know the bearing stress of 140 kilonewtons per meter squared is not exceeded. So once the bearing pressure is okay, then we can use the ultimate limit state to design the concrete member. And the design axial load is given by 770 multiplied by 1.35 plus 1.5 times 330. So you can see it comes to 1534.5, and the design moment comes to 156.3. So we can find the maximum stress under the footing and minimum stress under the footing. The maximum stress is axial stress plus bending stress. Minimum stress is axial stress minus bending stress. So you can see we'll get a stress distribution like this under the base, and there are important points. And one is, what is the stress and effective depth away from the face of the column. The other one is, what is the distance from the face of the column to the edge of the base. And this is 450, column is 450. The base is 3600, so one side is 1800 minus 225, so you get 1575 millimeters here. And 1575 minus 502 is 1073. And we know the stress values at these places as well: 145, 153, 166.1 here, 117.9. But we will not be worrying too much about this side, because this side is more critical than this side, unless the moment reverses. So you can find the moment at the face of the column, and the moment at this place is, the stress is 145, and you are multiplied by the width of the base, that is 3, and then this distance is 1.575, and distance to the centroid of that is 1.575 divided by 2. And then you have to consider this triangular portion. For the triangular portion, the height of the triangle is 166.1 minus 145, which is 21.1. So the area of the triangle is half 21.1 multiplied by 1.575, and then you have to multiply it by the width of the base, that is 3 meters, because the stress is acting over the full width of the base. And then we have to see the distance to the centroid of the base is 2/3 times 1575. So you can see 145 multiplied by 3, 1.575 squared divided by 2 plus 0.5 times 21.1 multiplied by this projection 1.575 multiplied by the width of the base and 2/3 times 1575. That will give the total bending moment due to all these variable loads, variable stresses, and linearly varying stresses. So the bending moment is 591.9 kilonewton meters. And if you are using 40 or 50 millimeter cover with 16 millimeter reinforcement, here I have considered that we will be using 40 millimeter cover, and the effective depth is 502 millimeters. And from that, we can work out M over FCK BD squared, and it is 0.031, and you can see these very low values will end up with an effective depth of 0.95D, because actual value is 0.97D, and we can get a value of 0.95D. And to find the value of Z, we can substitute in this equation that we derived last time. And the value of K is this one. K is MO FCK BD squared, and it is 0.031. And here you can see the effective depth is governed by 0.95D rule, which is 476 millimeters. So when you know the effective depth, we can find the reinforcement, and we'll end up with 2858 millimeters squared. The moment you find the reinforcement, you have to check the minimum reinforcement as well. And the minimum reinforcement is given by this equation. And once you calculate the minimum reinforcement, it is depends on FCTM. FCTM is given as a function of the strength of concrete, and FCTM is 2.59, and Once you substitute in this equation, you can find the value of the minimum reinforcement, which is 0.0013 BTD, but I have got the answer as 0.134. And you can see the minimum reinforcement is 2018, whereas we need 2858. So we'll provide this amount of reinforcement, which means provide 15 bars of 16 diameter. 15 bars of 16 diameter. And then the moment you have a large rectangular base or large square base or a rectangular base, it is important for us to see whether we have to have a concentration of reinforcement over 3D plus the size of the column, over 3D plus the size of the column. And there's a guideline. The guideline says, you know, if the base is large, then the pressure distribution, although we assume it to be uniform, it is not uniform. There will be more pressure directly under the column than away. So because of that reason, whatever the reinforcement you calculate, provide more reinforcement, more of that within a small band on either side of the column, and the remaining portion of the reinforcement can be provided beyond this point. So we have to actually see what is the condition. Condition is if the width of the base is greater than 1.5 times Cx plus 3d. If the width of the base is greater than 1.5 times Cx plus, Cx means size of the column, plus 3d, then provide 2/3 of the reinforcement within a band like this, So we have to see whether we comply with that particular rule when you are providing reinforcement. So what we do is, this is the detail given here, the reinforcement in footings, and this is the guideline given in the handbook by Institution of Structural Engineers. And there they have directly specified this minimum of 0.0015 BH, considering 30 megapascal concrete. But if you are using a different concrete, you can calculate the minimum reinforcement to be provided. And then Lx greater than 1.5 times Cx plus 3d, then you have to provide 2/3 of the reinforcement calculated over Cx plus 3d, Cx plus 3d. Within this band, all that reinforcement should be provided. So if you calculate Lx, that is 1.5 times Cx plus 3d, you see it's 2934, whereas the width of the base that we have is 3000 millimeters. The width of the base that we have is 3000 millimeters, and we are providing the reinforcement in that direction. So the reason is we are providing the reinforcement this way, and the question is whether we have to have a concentration of reinforcement. So to decide on that, you have to see this reinforcement is provided over width of 3 meters. So we have to calculate what is Lx in that direction, and the value of Lx is 2934, which is very close. But still the width is more. So if you want, you can ignore this because claim that 2934 is pretty close to 3000 and just provide the uniform reinforcement. On the other hand, you can decide to have a concentration of reinforcement. And if you are going for a concentration of reinforcement, you can look at this rule Cx plus 3d, that is 450 plus 3 times 502, 1956. And we are providing 15 bars. So 2/3 of that is 10 bars. 10 bars can be provided over this. So we can go for a spacing of around 200 millimeters for over 2/3 of the width, and the remaining part we need 15 bars. So instead of 15 bars, we can provide 16 bars, 10 within the band, 3 on either side. So altogether, so the overall width is 3000 millimeters, and the width of the band is 1956 millimeters, which means approximately 525 millimeters will be on either side of the band. So over 525 millimeters, we have to provide 3 bars. So again, you will find the spacing may be about 250 or 260 millimeters. The reason is, over 500 millimeters, we are providing only 3 bars. So you need to have a spacing close to 250 millimeters. So within the column band, we get T16 at 200 centers, and beyond that we can get T16 at 250 centers. So is that clear that you have to have a concentration of reinforcement when the width of the base is large? So now we can have a look at the short span moment. So when you consider the short span, now these are longer span, 3600. In the other direction, the stresses are changing, but we are interested in the bending moment. So because we are interested in the bending moment, what we do is we'll take the average of these two values, and then find the bending moment when you have a projection of 1500 from the center of the column. When we have a projection of only 1500 millimeters from the center of the column. So we have to check the short span direction, and when you check the bending moment in the short span direction, we'll be using the average stress rather than the maximum stress, and distance from the face of the column is 1275 millimeters. So the bending moment will be 142 is the average stress multiplied by the width of the base. Now it is the length of the base, 3600, multiplied by 1.275 square divided by 2, ending up with 415 kilonewtons per kilonewton meters. Again the same story, and you will need this amount of reinforcement, and when you calculate the minimum reinforcement in that particular direction, you will find that you need 2354 millimeters squared, because the minimum reinforcement quantity will depend on the width of the base, and the width of the base is more in this particular direction, 3600. Then you will end up with 2354 millimeters squared, which means the minimum reinforcement is governing. And 2354, and if you are providing 12 millimeter bars in the shorter direction, then we need about 21 bars, and 2/3 of that is of 21 of 12 millimeter bars. And when you calculate this dimension, limited dimension, it is 2934 still. Sorry, should be multiplied by 488. So anyway, it's close to this. But whereas the width of the base is 3600, so that means we have to definitely have a concentration of reinforcement. So 2/3 of 21 bars is 14. So we have to provide 14 bars over width close to this. So if you provide 14 bars over something like 2934 divided by 14, you can see that we can provide the reinforcement at 1956 divided by 15 bars, 14 spaces, or 15 spaces, we'll go for that. 1956 divided by 15 spaces. You'll end up with something like 125 centers, and you can have 3 bars on either side, 3 bars on either side, and then you'll find that you can provide the remaining bars at around 250 centers. So basically, in that direction also you can have a concentration of reinforcement. Then we have to look at the vertical shear. Vertical shear is given by at a distance d. So that is vertical shear is equal to 166 plus 153 divided by 2 multiplied by 3 meters multiplied by 1.073. The shear force can be found straight away. It's not a big problem. That is average value multiplied by 3 multiplied by this 505 kilonewtons. And if we don't like to provide any reinforcement, so we have to find what is the shear carrying capacity. And the shear carrying capacity can be found from the table, or we can find it directly. And if you are finding it directly, we have to substitute the effective depth here and find the K value. CRDC is 0.12. And the reinforcement ratio also should be found, and then the FCK value, and then it should be more than the minimum shear as well. So if I use rho 1 value, which is 16 bars of 201 divided by BD 0.00178, substitute in this equation 0.321, and I can also find the minimum shear capacity of concrete. The minimum shear capacity of concrete is 0.36, so there's no point in worrying about this value because the minimum shear carrying capacity governs. So the actual minimum shear force that this particular section can carry is the shear stress multiplied by the area, and that gives a value of 542, whereas when we calculated the shear force, we found that is 505. So the actual shear force acting is 505, but the shear carrying capacity is 542, so we don't have a problem with direct shear. And in the other direction, again, what we do is we'll make use of the average. This direction, the other direction, again we'll make use of the average stress. We'll make use of the average stress and then find the shear force. And the projection on that side will be 3000 divided by 2 minus 225, that is the half the column size, minus effective depth, which is 488 millimeters. So you can see that vertical shear in the short span direction, here you get 3 meters minus half the column, 3 meters divided by 2, half the column size, effective depth, giving a total shear force of 102 kilonewtons. And when you calculate the capacity, again the capacity is governed by the minimum value. and the capacity is 632 kilonewtons, whereas the shear force is 402. So again, you cannot have any shear failure due to direct shear in the shorter span side. So longer span side is safe, shorter span side is safe against shear, and we don't have to provide any shear reinforcement. Now we are going to look at the punching shear, which is important because now the punching shear is slightly different. The reason is, if you look at three-dimensional stress variation of this particular base, and we know on this side we get a higher pressure, on this side we get a lesser pressure, on the sides it's varying, so now we have to see how we check the punching shear. So the punching shear requirement can be checked, punching shear, where the support reaction is eccentric with regards to the control perimeter. What we say as support reaction being eccentric is a bending moment is acting on that particular section. So before I move on to this punching shear, do you want to ask any question on this calculation so far, which is fairly straightforward, and we are just repeating the same calculation that we have looked at earlier, but now we are going to look at something little special. Now here what happens is, we are having a bending moment acting on the base in addition to the vertical downward load transferred through the column. Because of that reason, there can be the forces under the foundation are also varying. In addition to that, the shear stress distribution is also varying. So if the shear stress distribution is varying, we cannot simply say the shear stress is given by shear force divided by the punching shear perimeter. So we have to take account of the fact that shear stresses are varying, and that the fact that shear stresses are varying is taken into account by beta, and beta is given by 1 plus a value. And generally this value may be about 0.15 to 0.25. Generally this value may be about 0.15 to 0.25. It's a general statement. So we expect it to be around 0.15 to 0.25. So you will find now with beta being equal to 1.25, we are actually increasing the stress, increasing the shear stress to take account of the fact that the shear stress distribution is not uniform. Shear stress distribution is not uniform. So what will happen if shear stress distribution is uniform? That means only the case where we have only the axial load. If you have only the axial load, then beta is 0, beta is 1. But if you are having a bending moment and the axial load, then beta could be more than 1. Generally it lies between 1.15 to 1.25. But other values also might be there, but generally it's a trend. So we have to find this beta value. To find this beta value, we need to know the bending moment acting. We need to know the perimeter at which we are checking the punching shear. And we have to calculate the parameter called W1, which actually takes account of the variation in the shear stress and the shear force that is acting. So in addition to that, there's a value called K, and K has to be obtained from this table, and these are all from Eurocode 2. And you can see when you have a square column, the K value is 0.6. When you have a square column, K value is 0.6. So K value is 0.6. We have to find the bending moment. We also need to know the the axial load or the load that can cause punch shear. And we need to know the control perimeter that we are going to do the checking. And we also need to know what is this quantity W. This quantity W is given by E is the distance to the perimeter and dl, integration over the perimeter length. So if you have a square column, then once you perform that integration, you'll find the answer is given by this, where C1 is this dimension of the column, C2 is this dimension of the column, but in our case it doesn't matter because we are dealing with a square column. But if you are having a rectangular column, and you can also see the bending moment is acting in this direction. Bending moment is acting in this direction. Then W1 will be given by this particular equation, which is given by C1 squared divided by 2 plus C1 C2 plus 4 C2D plus 16D squared plus 2 pi D C1. And C1 is this particular dimension. So then it also says, when you are dealing with punch shear resistance of column bases, first you have to verify at the control perimeter 2D, and then the punching resistance of column bases should be verified at control perimeters within 2D as well. Within 2D as well. So that means, you have to check the punching shear resistance not only at 2D, that is the critical perimeter or control perimeter. We have to check the punching shear stress at the inner control perimeters as well. So basically what we do is we check the punching shear resistance from D to 2D, from D to 2D. And the reason for all this is, depending on the punching shear perimeter area, we get a reduction in the upward, we get a reduction in the net vertical load that can cause punching shear. So when you are using this equation, we are asked to use a value called VED reduced. And that's what we calculated in the earlier example, where we had a vertically downward force and an upward thrust. So we took the difference of those two. So similarly, it has to be done. But if you are checking at a perimeter inside 2D, then we have to use this increase in shear resistance given by 2D over A. So basically, if you are checking a perimeter at a distance D away, then A is equal to D. That means the shear resistance will be twice the normal shear resistance. The reason is, as you come close to the support, it will be increasingly difficult to create a shear failure. It will be increasingly difficult to cause a shear failure. So because of that reason, we have the enhancement for shear resistance. We have an enhancement for the shear resistance. And in certain other locations of EC2, this will be given as a reduction in the applied shear. But here in this particular equation, it has given as an enhancement for the shear capacity. Enhancement for the shear capacity. Even the V minimum value has been multiplied by that particular one. So basically, if A is equal to D, then you will find the shear capacity is double. Shear capacity is double. So in the case of a perimeter that is loaded eccentrically, eccentric loading, the punchy shear stress is given by VED reduced divided by the punchy shear perimeter divided by the effective depth. That will give the area of the punchy shear perimeter. multiplied by this beta factor, which can be about 1.15 to 1.25. So this way we are going to end up with a higher stress, higher shear stress due to punching shear than the axial loading case. So if you look at the numbers now, the axial load is 1.35 times permanent load plus 1.5 times variable load. The design moment is again 1.35 times permanent moment plus 1.5 times variable moment. So you'll find that the design moment is 156.3 kilonewton meters, whereas the design axial load is 1534 kilonewtons. And to find this VED reduced, we need this value of 1534.5. So punching shear resistance is determined at a distance d. So I'm going to determine the punching shear resistance at a distance d. The reason is, if you look at the size of the base is 3 meters by 3600 millimeters, and then the effective depth is about 500 millimeters. So we have to get another 1000 millimeters beyond that. So when you consider a perimeter at a distance around 1000 millimeters from the face of the column, you will find that, you know, the perimeter is so close to the edge of the base that we will have very small punching shear force, because, you know, the size of the base is 3 meter by 3.6, and the effective depth is about 500 millimeters, So 2D is 1000. So one side is 1500, whereas the punching shear perimeter is at 1225. So you can see only a very small area is left to cause punching shear failure. So which means the punching shear failure at 2D is very remote. So because of that reason, I decided to check the punching shear at D. So generally, if you are doing a design, you are supposed to check 1.5D, D, 1.5D, and 2D. So if you check about three perimeters, you will be able to see whether there's any problem. So basically, if you are checking at a perimeter D away, then you have to substitute. Now, this is the perimeter this is the value of W1 when it is located 2D away from the face of the column. So all these D terms, you can say, if you substitute, if you take it as 2D, then you can say force C2D is 2C2 2D, and instead of 2D, you can substitute the value of A. Then you will end up with, here you will end up with 2C2A. Here you will end up with 2D is equal to A. So you get 4A squared, and 2 pi DC1 will be pi A C1. So you will get an equation like that. So you can see pi A C1, 4A squared, 2C2A, C1, C2 will not, has no D term, so it is not affected. So you can see, you can get a value for control perimeter. At the control perimeter for W1, you can get a value for at the control perimeter for W1, and that will be given by a parameter called A, and A is the distance from the face of the column. A is the distance from the face of the column. And if you take the average effective depth, it is 495 millimeters, and C1 is equal to C2 is equal to 450, and so at a distance D, we can find the length of the punch and shear perimeter, and also we can find the area inside the punch and shear perimeter. So area is 1.86, length is 4.9 meters. So and in addition to that, when you are checking for punch and shear, we have a situation where the stresses are varying. So punch and shear perimeter is going right round. So what we do is we take the average pressure, that is 117.9 plus 166.1. We take the average pressure. Here you can see, we take the average pressure of 142, and then we calculate the V reduced by using that particular average pressure and the area over which that is acting within the punch and shear perimeter. The area within the punch and shear perimeter is 1.86. So you have a load of 1534 acting downwards, an upward pressure of 1.86 multiplied by 142, or an upward thrust of 142 kilonewtons per meter squared acting over 1.86 square meters. So you can see the reduced punch shear stress will be 1269, and similarly you can calculate the value of this W1, which comes to 2.43 meters. So you know the value of W1, we know the value of U is 4908. We know the effective depth, average value as 495 millimeters. We know the moment, we know the value of moment because moment is already given, which is the maximum moment, 156.3. And in addition to that, we know the reduced V value. Reduced V value is 1269. So because all these values are known, we can actually calculate the punch shear stress. We can actually calculate the punch shear stress. So the punch shear stress will be equal to V reduced is 1269. You know the punch shear perimeter, you know the effective depth. The K value is 0.6. The moment is known. V reduced is again coming here. And the value of W is 2.43 millimeters. Whereas the value of U is 4.908 meters. So once you substitute all those values, then you will find this quantity is equal to 1.149, and I said earlier it would be around 1.15 to 1.25. So you can see we are getting a value close to 1.15. So when you get the answer for all this, you see the answer is 600 kilonewtons per meter squared, or 0.6 newtons per millimeter squared. 0.6 newtons per millimeter squared. So this is how you can calculate the punch shear stress when you get a bending moment and an axial stress. And here you can see what we do is we simply calculate the punch shear stress, and then we modify it by a factor, and in this particular case the modification factor is 1.149, and the modification factor can be calculated this way. The only long calculation is in W1, because calculating the perimeter is not a major problem. So any question on this? Can you understand it? So once you do that, we have to check this 0.6 newtons per millimeter squared with the shear stress acting on the punchy shear perimeter. And in this particular case, A is equal to D. That means the punchy shear resistance will be twice the value given by the basic equation. And in this particular example, we have seen that the shear capacity is not determined by the reinforcement and the depth. It is determined by the minimum value for shear strength. And the minimum value for shear strength we found earlier as 0.36. And then A is D. So the shear resistance will be 0.36 multiplied by 2. 0.36 multiplied by 2, it is equal to 0.72. So on a punchy shear perimeter located D away, the shear stress is 0.6, resistance is 0.72, which means the base is not likely to fail due to punching. And in a real example, you should be checking at other perimeters as well. So you can check at 1.5D away from the face of the column, and also at 2D away from the face of the column. But in this particular problem, when you consider 2D value, and you will see that 2D is pretty close to the perimeter of the base. So in such a situation, the vertical loads acting to cause punchy shear will be very small. So that's why I checked at D, but I should be checking at 2D as well. Even if they are smaller, still I have to check at 2D as well. So in this particular example, I have checked only at D, because I wanted to highlight all these different parameters, and you can check at 2D as well. Is that clear? So generally you can write a spreadsheet, because these are standard calculation, and you can get you can check between D and 2D.